Did you know that over 175% more children have been diagnosed with Autism Spectrum Disorder, ASD, in the last decade? While early intervention is critical, traditional diagnosis methods are time-consuming, expensive, and often stressful for families. But what if we could simplify this process using AI and the way our eyes move? Today, we're diving into a groundbreaking study that's redefining how we detect ASD, using eye gaze as a key clue. Let's start with the basics. ASD affects how people communicate, focus, and interact socially. Current diagnostic tools like the ADOS or ADIR require hours of in-person assessments by specialists. But what if we could use something more accessible? Enter eye tracking, a technology that maps where people look. Researchers have long noticed that children with ASD often show unique patterns, like avoiding eye contact or fixating on objects instead of faces. But how do we turn these observations into a reliable diagnostic tool? This study introduces an AI system that analyzes image transforms derived from eye tracking data. Think of it like converting eye movement data into visual maps. They tested 3 types of transforms: heat maps, showing where eyes linger, scan paths, tracing the journey of gaze, and fixation maps, highlighting where eyes stop. By training a neural network, specifically GoogleNet, on these images, the system learns to spot subtle differences between children with ASD and those developing typically. Here's the cool part: the AI doesn't need raw video footage. Instead, it uses transformed images that anonymize data, protecting privacy. For example, a heat map might show a child with ASD has more scattered eye movements, while a typically developing child's heat map is more concentrated. These patterns, when analyzed by the model, can flag potential ASD traits early. The results? The system achieved high accuracy in distinguishing between the two groups, all while keeping sensitive data secure. This could mean home-based, regular screenings, reducing stress and enabling earlier interventions. Plus, it opens new ways for parents and therapists to track progress without invasive methods. Now, let's dig deeper into the technical heart of this breakthrough. The study leverages image transforms to extract meaningful features from raw eye-tracking data. These transforms act as a bridge between raw behavioral data and machine learning models. For instance, heat maps encode fixation density, scan paths capture temporal sequences of gaze, and fixation maps highlight spatial distributions. But how do these transforms actually work? Enter the continuous wavelet transform, CWT, and fast Fourier transform, FFT, 2 mathematical tools that reveal hidden patterns in data. CWT is like a multi-scale magnifying glass, analyzing both the time and frequency components of eye movement sequences. It uses wavelets, which are small, oscillating functions that adapt to the data's structure. For example, the Haar wavelet, a simple yet powerful wavelet, can detect abrupt changes in gaze patterns, such as sudden shifts in attention. FFT, on the other hand, breaks down data into its frequency components. Imagine analyzing a song. FFT would identify the individual notes, frequencies that make up the melody. Applied to eye-tracking data, FFT reveals dominant spatial frequencies in heat maps or scan paths. For instance, children with ASD might show higher concentrations of high-frequency components in heat maps, while scan paths exhibit broader, lower-intensity distributions. These transforms aren't just theoretical, they're practical tools that enhance model performance. When researchers applied CWT and FFT to the eye-tracking data, they uncovered subtle differences that traditional methods missed. The transformed data was then fed into neural networks like GoogleNet and AlexNet. The results? Scan paths processed with CWT achieved up to 85% accuracy in distinguishing ASD from typical development. Why? Because scan paths inherently encode the temporal dynamics of gaze, and CWT amplifies these patterns by adding spectral details. But the study didn't stop there. They also used data attribution to identify which parts of the eye-tracking data were most critical for diagnosis. Think of this as the AI asking, "What exactly am I noticing that makes me think this person might have ASD?" Then, they applied model distillation, a technique that simplifies complex models into lighter, faster versions without sacrificing accuracy. This makes the system more practical for real-world use. So what does this mean for the future? It's a step toward more accessible, ethical, and efficient autism diagnosis. By turning eye movements into visual stories, AI is helping us see autism in a whole new light. And that's pretty amazing.